Thank you.
All right. So gathering sufficient data using a single long simulation can take an extraordinary amount of time. So if we're interested in observing a protein folding event or allosteric transition, a single simulation on a desktop computer could take over 1 million years to simulate. Now, fortunate for us, there are a few other methods to getting at long timescale phenomena that preserve kinetics. And it should be no surprise that these use Markov state models. So a very important feature for Markov state models is that they're a rigorous statistical framework for piecing together many parallel simulations. So we can run lots of simulations in parallel and get at timescales much longer than any individual simulation. But these starting structures don't need to be the same structure. In fact, we can choose where in conformational space we simulate from. And there's been some good introductions to adaptive sampling, so I don't think I need to belabor this too much. But we can start a swarm of simulations from some starting state. And they'll explore around this state. We can build a Markov state model, select new states to simulate, and iterate through this process. Now, there are a number of different ways we can select states, and typically we rank and select states based on some statistical components, either ranking states based on their contribution to uncertainty in the Markov state model, or in their ability to explore and discover new and exciting states. And recently, Greg and I developed another kind of method we call this fluctuation amplification of specific traits, or FAST. So here we leverage structural information in our ranking and selecting of states. So this attempts to follow conformational gradients to optimize specific structural traits. Here we rank states by balancing their ability to exploit some promising structural feature and their ability to explore conformational space. And this can it's pretty versatile. We can add different ranking functions for a variety of different problems. And we've previously shown that for one problem in particular that I'll talk about, discovering large pocket volumes, we can use the solvent accessible surface area, or SASA. And we've shown that it can quickly discover a diversity of large SASA states. We can discover large SASA states with at least an order of magnitude less simulation than count-based adaptive sampling, and many orders of magnitude less simulation time than conventional simulations. So I just introduced a few different equilibrium-based sampling methods. We have long simulations. We can run simulations in parallel. We have adaptive sampling, such as counts-based adaptive sampling, and our FAST algorithm. So these are all equilibrium-based sampling methods, so their estimates of transition probability should remain unbiased. One question that we have is, how do each of these methods explore conformational space? Particularly, does adaptive sampling and FAST provide accurate transition pathways? So the only real difference between these different methods is in the probability of the sets of states that they discover. So could these differences in probability of discovering different sets of states actually influence predictions of transition pathways? So to really get at this, I decided to take it down to the basics and just really understand how varying sampling parameters influence a state discovery on very simple landscapes. So to that end, I developed an analytical expression for relating the probability of discovering states on a landscape to the length and number of simulations that are used. So here on the right, I'm plotting the probability of discovering states 2 and 3, starting from state 0 for a single long simulation, so that's in the solid line, and many parallel simulations, that's the dotted line. And as you can see, the probability of discovering states 2 and 3 for many parallel simulations can be significantly lower than a single long simulation. Now, that's because the probability that a long simulation can make successive hops is higher than any one of the parallel simulations making all these successive hops. Now, this isn't just based on how I've constructed this landscape. In fact, we can see the same property with a fully connected landscape. The probability of discovering state 2 from state 0 for a long simulation is higher than many parallel simulations. So from this, you might conclude, well, maybe long simulations are just better at exploring landscapes, but that's not the case. It's definitely dependent on the landscape. I can construct another landscape that has many arms, much higher dimensions, and on this type of a landscape, parallel simulations have a significantly higher probability of discovering states than long simulations. So it's really dependent upon the landscape that we're sampling on how different methods will perform. So with that in mind, we decided to model a few different landscapes physically inspired by some real challenges in molecular dynamics simulations and run kinetic Monte Carlo simulations on these landscapes to characterize performance of different sampling methods. So here's the first landscape that we developed, and this is based on the challenge of trying to fold a protein. This is a simple folding funnel landscape. So here we have high energy in red, down to orange, yellow, and blue, lower energy. And we have a starting conformation. So this is like an unfolded state, and we're trying to get to this target conformation. So the highest flux pathways on this landscape are denoted by these solid lines. And we ran 4 different sampling methods. So we ran a long simulation, parallel simulations, count-based adaptive sampling, and fast. And first, we can characterize the probability of just discovering states on this landscape for each of the sampling methods. And the first thing that pops out is that each sampling method has a unique state discovery signature. They each explore the landscape pretty differently. So long simulations kind of diffuse around, and this is the probability of discovering a state before reaching the target. Long simulations can diffuse around and discover a lot of states before reaching this target state. Parallel simulations very thoroughly explore around the starting state, but have a low probability of ever reaching the target. Count-based adaptive sampling spreads out on this landscape quite a bit, discovers a lot of states, has twice the probability of discovering states on the edge here than long simulations, but half the probability of discovering the target. And our fast simulations are very directed. So they can cut across the landscape and actually have the highest probability of discovering the target state. Now, this is just in the probability of discovering states. Since each of these simulations are in local equilibrium, their estimates of transition probabilities are unbiased. And if we look at the probability that each state is predicted to be on pathway from the start to the target, they all predict the same pathways on this landscape. So this is nice for a very simple folding funnel where the highest flux pathway is kind of a direct line from the start to the target. We want to see how well can adaptive sampling and fast actually navigate around barriers. So what happens if you have some obstacles in your landscape? So we constructed another landscape up here on the top left. Again, I'm showing the highest flux pathways from the start to the target structure. And you can see there's a large energy barrier here, another one here. And in addition to this dominant pathway, there's an alternative path. So we're interested, can adaptive sampling and fast actually find both of these paths with reasonable probabilities? So these plots, again, are the probability that any state is predicted to be on pathway from the start to the target. And the long count-based adaptive sampling and fast all produce very similar results. The adaptive sampling and fast show that they do, in fact, navigate around these barriers and show the probability of predicting this path relative to what we'd expect. So from this, we can we conclude that on this landscape, adaptive sampling and fast do, in fact, navigate around these barriers and find reasonable pathways. But we want to make this a little more challenging. So we construct another landscape where we have a very large energy barrier between the start and the target. So this should be a pretty challenging landscape for fast because for our directed component, we're using the distance to the target state. And it's going to actually have to sample from states that don't make progress on its order parameter. It's going to have to select from states that actually go away from the target. And so before we look at that, we can look at the probability of discovering states and pathways for the long simulations. In fact, they do go around this barrier. The predicted paths all go around the barrier. Interestingly, if we look at parallel simulations, there's a very low probability of discovering states that go around this barrier. And there's a higher probability of discovering the set of states that go across this barrier. So this incorrectly leads the prediction of the highest flux pathway to jump across the barrier. I think this is a pretty interesting result that just changing the length and number of simulations can actually affect the apparent transition pathway that you see. So we name this phenomena pathway tunneling, which is essentially just observing a less probable transition path as like a result of sampling artifacts. So we were curious if adaptive sampling and fast show a pathway tunneling on this landscape. So our count-based adaptive sampling, it goes around this barrier and reasonably predicts paths that go around this barrier. So our count-based adaptive sampling avoids tunneling. Fast also has a high probability of going around the barrier and a slight probability of discovering the set of states along the barrier. So we do see some predicted paths going across this barrier. So to alleviate this problem, we came up with another method, so where we calculate the highest flux pathways from the start to the target and sample from states along these highest flux pathways to refine their transition probabilities and discriminate between alternative paths. So when we use FAST to get to the target state and then refine transition probabilities, we see a significant improvement in our predicted pathways from the start to the target. So we call this method, so it's inspired by the string method. So this is using equivalent aggregate simulation time than the long simulations can discover the target state with a very high probability, the highest probability, and gives a reasonable pathway. And I should also mention that the estimates of transition probabilities along these highest flux pathways are the most accurate for FAST with the string method. So I've kind of shown how sampling works on these very simple landscapes, but I want to test this out using all-atom molecular dynamics simulations, particularly how will this FAST produce realistic transition paths. So we decided to try to simulate the folding of the lambda repressor protein. We ran a lot of parallel simulations, long simulations, and fast contacts, where our structural metric is the fraction of native contacts present in the crystal structure of this lambda repressor. So from the parallel simulations, we get 700 microseconds of aggregate simulation time, but we do not see a folding event. From our long simulations, we have about 40 microseconds of simulation, and we do see a folding event. And with FAST, we see a folding event in 4 microseconds, which is pretty remarkable that the folding time of this protein experimentally is on the order of around 9 microseconds. So I'm showing the highest flux folding pathway of the lambda repressor for our fast contact simulations on the right here. And we can look at this pathway in a little bit more depth. So what I'm showing here is the RMSD between the backbone angles along the highest flux pathway for 2 runs of our fast contacts and long simulations. This is the backbone RMSD for each residue. And from here, we can see that our fast contact simulations predict that helices 1 and 4 fold before helices 2 and 3, which is in agreement with the long simulations that we observe. So these are often the same starting structure, too. And this is consistent with previous simulation reports of the lambda repressor, and also agree with hydrogen deuterium exchange data that suggests that helices 1 and 4 fold before helices 2 and 3. So it seems that fast contacts is producing a pretty realistic folding pathways with a very small amount of aggregate simulation data. Now I should also mention that Go models were used to fold this protein, and the Go models predict that helices 1 through 4 all fold simultaneously. So it's nice that our fast contacts is not an expensive Go model. So lastly, I want to say that I think I'm running out of time, but I just want to say that FAST, in addition to providing really realistic transition paths, it can also build very predictive models. So I just want to kind of highlight this story where we're looking at, there's this mutation in 10-beta lactamase that is extremely stabilizing. But if you look at the crystal structure between these 2 sequences, there's no real change. It's less than 0.6 angstrom RMSD difference. So we used FAST to try to build this physical model of what could be happening from this mutation. And so we started looking at distance distributions, and we came up with this physical model and came up with predictions for a few designed sequences that turned out to be very predictive experimentally. So I don't have time to talk more about this, but please talk to me if you're interested. So just to conclude, I trying to give a good physical intuition for how sampling affects state discovery on complicated landscapes, or simple and moving up to complicated landscapes, and find that varying the length and number of simulations can drastically affect the probability of discovering different sets of states. Adaptive sampling and FAST can navigate around barriers, and largely I think it pays to be pretty adaptive to adaptively sample across conformational space and really pick and choose where we're spending our computational resources. So this is a fast simulation up on the top here on this landscape, showing how it kind of explores the landscape compared to a single long simulation, which just diffuses around. So with that, I'd like to acknowledge everyone in the Bowman Lab, particularly Greg, Justin, and Leos, funding. And with that, I'll take any questions. So thank you.
So yeah, I have a kind of a comment and a question. The comment is that, so this finding seems surprising that the many numbers of parallel simulations show different behavior. But if you take it to its extreme, it makes sense. You know, a trillion time-step simulation is going to show you something different than a trillion one-time-step simulations, right? So the question is, have you looked at the transit times of these systems compared with the waiting times of the transition, and shown how that depends, or how that kind of maps up with the length of the different parallel simulations?
So by transit time, you just mean the rate at which something jumps across barriers?
So the waiting time is like the mean first passage time. The transit time is, okay, I've left basin A, so all the time that it takes for me to actually get from basin A to basin B.
We're relating to like probabilities of discovering different sets of states. I'm sorry, can you repeat the?
So you're running all these parallel simulations, but you haven't told us how long they are, right?
Right. So
how does that time length compare to the transit time that it takes to get from A to B?
So right. So the parallel simulations that I've been showing on the simple landscapes all are long enough to reach the target states in question. They have very low probabilities of discovering these target states, but they're not so short that they can't reach the target state. Does that answer? I don't have specific numbers for the mean first passage times.
So yeah, it'd be interesting to see a more kind of quantitative analysis on something that kind of looks a little biophysical, where you have two basins, let's say.
I think in this case, the shorter simulations are like on the order of like 10% of the global relaxation time scale. So you have some chance of reaching.
So I think we need to stay on time. I'd like to thank Max again and introduce